Lost and Pound is a 1v3 minigame in Super Mario Party Jamboree. In it, the team of 3 attempt to repeatedly bonk the solo player with a giant mallet, giving them severe head trauma and ending their friendship once and for all. The solo player has recourse in being able to hide from the other players and avoid getting bonked. The team of 3 has only 3 rounds to bonk the solo player a total of 3 times, but unless they're good at reading their opponent, success is just a matter of luck, right? Well, if it was, I wouldn't have made this video, is what I'd like to say, but after spending hours doing the math and recording and editing footage, I don't have faith in my ability to resist the sunk cost fallacy. But what I do have faith in is the power of math, probability, and numbers, so today I'm going to use those things to show you the optimal strategy to bonk your friends. At its surface, Lost and Pound is a pretty simple game to understand. The game is split into 3 rounds. In each round, the solo player will choose one of 4 hiding places. Then each member of the team will guess which hiding spot the solo player chose. Each correct guess results in a bonk. The team wants to bonk the solo player a total of 3 times, but these bonks can be split across the 3 rounds, or all in a single round. While the game doesn't provide any way to know where your teammates are planning on bonking, if you're sitting next to each other on the couch, or you're all in a voice call over Discord, then the team gains a huge advantage with the ability to communicate and coordinate. Assuming you aren't still yelling at each other over that star steal. Now, if you and your friends do coordinate, you generally have 3 options. First, you can all spread out, with each team member choosing a different hiding spot. This gives the highest chance of getting a hit in, but the best that you can do is get a single bonk on the solo player. The second option is for everyone to choose the same spot. If the team guesses correctly, they'll be rewarded with 3 bonks on the solo player, winning the game right then and there. But this also carries the lowest chance of actually hitting the solo player. The third option is for 2 team members to double up on one space, while the third team member chooses a second space. There's a better chance of getting a hit in than when everyone triples up, but not as good as when everyone spreads out. However, there's a chance of getting 2 hits in a single round, more than when everyone spreads out, but less than when everyone triples up. So which of these is the best play to make? Without any knowledge of the solo player's habits or play patterns, we can turn to math. Side note, we can also turn to math if we do have knowledge of the solo player's habits and play patterns, but the math gets a bit more complicated since it involves doing a statistical analysis of that player's past games. And unfortunately, using stochastic methods to analyze your friends is unethical. So let's start with the basics and look at the probabilities for each individual play. If the team spreads out, each choosing a different space, then they've covered 3 of the 4 possible hiding spaces. This gives them a 3 out of 4 or 75% chance of hitting the solo player. If the team triples up on a single space, they only have a 1 in 4 or 25% chance of hitting the solo player, but they'll get 3 hits if they're correct. One way we can compare these plays is with expected value. Basically, if we repeat the same play multiple times, on average, how many hits does that play score each round? So for spreading out, there are 2 possible outcomes. Either the solo player gets hit once, or they don't get hit at all. The first outcome has a value of 1 bonk and a probability of 75%. The second outcome has a value of 0 bonks and a probability of 25%. So we have an expected value of 1 bonk times 0.75 plus 0 bonks times 0.25, which equals 0.75 bonks. Compare that to tripling up, which also has 2 possible outcomes. Either the solo player gets hit 3 times or not at all. Getting hit 3 times is a value of 3 bonks and a probability of 25%. And evading the bonks has a value of 0 bonks and a probability of 75%. So the expected value of tripling up is 3 bonks times 0.25 plus 0 bonks times 0.75, which comes out to, again, an expected value of 0.75 bonks. Finally, the team of 3 has the option to have 2 players double up and 1 player grab a different hiding space. This play has 3 distinct outcomes. In the first, the 2 players that chose the same space guessed correctly. This outcome has a value of 2 bonks and a probability of 25%. The second outcome is that the third player chose the correct space, giving a value of 1 bonk and a probability also of 25%. The third outcome is that the solo player chose one of the remaining 2 spaces. In that outcome, the solo player doesn't get hit, so the value is 0 bonks, and there are 2 out of 4 spaces that lead to that outcome, so its probability is 2 out of 4, or 50%. So the 2-in-1 play has an expected value of 2 bonks times 0.25 plus 1 bonk times 0.25 plus 0 bonks times 0.5, which, once again, comes out to 0.75 bonks. Okay, so each play has the same number of expected bonks. Does that mean that the plays are all equivalent? Not in the slightest. Expected value is just one way to compare different strategies. But it is never the only method, nor is it the best method. It's just a good starting point to lead into other methods. Let's look at the chance of winning the team has if they repeat the same play all 3 rounds. If they spread out, then they need to get a hit each round. The likelihood of getting a hit in a round is 75%. But what's the likelihood that they get a hit each round? Well, when you have a bunch of events happening and you want the probability that each event has a particular outcome, as long as the events are independent, you can multiply the probabilities of each outcome together. For example, if you have 2 coins and you flip them, you can find the probability that both land tails by multiplying the probability that the first lands tails by the probability that the second lands tails. Now, while each round isn't exactly independent, as the solo player may be more or less likely to choose a particular space based on the events of the previous round, we can pretend they're independent to make the math a bit easier. So if the team spreads out, each choosing a different hidey hole, then they have a 75% chance of hitting the solo player. If they do this 3 times, the likelihood that they get 3 hits is 3/4 cubed, which evaluates to 27 out of 64, or 42.1875%, which is a good bit worse than calling a coin flip. Obviously, this is a bad strategy. If the players spread out in round 1 and miss, then continuing to spread out can't win them the game since they only have 2 rounds left to get 3 hits. We can do similar math to find the probability of a team victory by repeating the other 2 plays, but going 2-in-1 has a similar issue. If you get to round 3 without having landed a single hit, then the 2-in-1 play can't win the game for the team. Tripling up at least can always win, but is repeating the riskiest play each round really the best strategy? Why not try changing things up, using one play in round 1, and choosing our plays for rounds 2 and 3 based off the results of the previous rounds? If we're going to change our play each round, let's start the final round and work our way backwards. After all, once the game gets to round 3, what matters isn't the exact plays that were made in the first 2 rounds. The only thing that matters is how many times the solo player got bonked. And since the game ends in victory for the 3 once the solo player has been bonked at least 3 times, we only need to look at 3 scenarios going into the final round. Has the solo player been bonked once, twice, or not at all? If round 3 ends with the solo player having been bonked 2 or fewer times, the solo player wins. You might get partial credit on your math exams, but Nintendo is much less forgiving. So if the final round starts and the solo player hasn't been hit yet, the only way for the team to win is by tripling up and praying to Miyamoto that they get that 1 in 4 chance of victory. If the final round starts and the solo player has been hit once, then spreading out will result in a solo player victory for sure. The best that the team can get is another hit for a total of 2 bonks, leaving them 1 bonk shy of the needed 3. But when it comes to going 2-in-1 or tripling up, there's actually no difference. The team only needs to get 2 more hits in, but the 2-in-1 play only accomplishes that 25% of the time. On the other hand, if the team gets 3 more hits in, while they don't get extra credit, they still claim a win, and so tripling up also gives a 25% chance of victory. But if the solo player has already been hit twice by the time that round 3 rolls around, then spreading out becomes the best play to make. The team only needs to land at least 1 more hit, and spreading out accomplishes that 75% of the time, while the 2-in-1 play only gets the win 50% of the time, and tripling up only wins 25% of the time. So keeping tally, if the final round starts with 2 hits on the solo player, the team should spread out for a 75% chance of victory. In both other scenarios, the team might as well triple up as they'll only have a 25% chance of victory. Now we move back in time to round 2. This is where the largest chunk of our work comes in, because the game can enter this round 3 different ways, the team having scored 0, 1, or 2 bonks in the first round, and it can exit in 4 different ways, with 0, 1, 2, or 3 bonks on the solo player. We'll split this into 3 scenarios, the round starting with 0, 1, or 2 bonks already scored on the solo player, and in each scenario we'll calculate the probability of each play leading to an eventual victory. Let's start easy and work with the scenario where round 2 starts with 2 bonks already scored in round 1. Obviously, the team should spread out for the best chance of victory. One more hit wins them the game, and spreading out gives a 75% chance of getting that hit. But what if they miss? That'll happen 25% of the time, and the game will go to round 3 with the solo player having been hit twice so far. This is why we're working backwards. We already know that if the game gets to round 3 with 2 hits on the solo player, the team has a 75% chance of winning by spreading out. So if we start round 2 with 2 hits on the solo player, what's the likelihood that spreading out will lead to a team victory? To calculate the exact probability, we can look at each outcome and multiply the probability that that outcome happens by the probability that that outcome leads to a victory, then add all of those products together. So if the players spread out, they have a 75% chance of getting a hit, which is a 100% chance of victory if it happens, and a 25% chance of missing, which leaves a 75% chance of winning in round 3. So we have 0.75 times 1 plus 0.25 times 0.75, which equals a 93.75% chance of victory. That's pretty good. We can do this calculation again for the other 2 plays, but the only thing that changes is the probability of winning in round 2 goes down, and the probability that the game goes to round 3 goes up, so the overall chance of victory will go down. Now let's look at the scenario where round 2 starts with only 1 hit on the solo player. In this scenario, spreading out has a 75% chance of sending the game to round 3 with 2 hits, and a 25% chance of sending the game to round 3 with only 1 hit on the solo player. The team will spread out in round 3 if it starts with 2 hits, but if it starts with 1 hit, then the team can either triple up or go 2-1, but both give the same 25% chance of victory. So in this scenario, spreading out to cover 3 different spaces has an overall chance of victory of 62.5%. Better than a coin flip, but much lower than the previous scenario. What about the other options? Unlike spreading out, the other 2 options have the chance to win the game in round 2, stopping the game from going to round 3 completely, so they might give a better chance of victory. If the team triples up, there's a 25% chance that they win the game right then and there, but a 75% chance that the game goes to round 3 with only 1 hit on the solo player, which leaves the team with a 25% chance of winning in round 3. So the probability of victory if they triple up is only 43.75%, not as good as spreading out. Tripling up relies too much on winning immediately, but since the team already scored 1 hit in round 1, that 3rd hit from tripling up isn't doing anything. Maybe the team should go 2-1. This gives the same chance of an immediate victory as tripling up, but improves the team's odds going into round 3. Now the team has a 25% chance of getting an extra hit, so that round 3 starts with 2 hits on the solo player. Again, this means that the team can spread out in round 3 for a 75% chance of victory. But the 2-1 play can still miss, though only at a 50% chance, and push the game to round 3 with only 1 hit on the solo player, and the team with a 25% chance of victory. So the results are 2 hits, 1 hit, or 0 hits, at probabilities 25%, 25%, and 50%, and chance of victory at 100%, 75%, and 25%, so the overall chance of victory for the 2-1 play in round 2 with 1 hit on the solo player is 56.25%. Better than tripling up, but still not as good as spreading out. So is spreading out the best strategy after all? Well, hold on, we still have one more scenario to look at. What if round 2 starts without any hits on the solo player? If the team spreads out, they have a 75% chance of getting a hit and a 25% chance of missing, but either way the game goes to round 3. And in either outcome, the team only has a 25% chance of victory. If the team goes 2-1, they can enter round 3 with 2 hits, 1 hit, or 0 hits. While getting 1 or 0 hits leaves a 25% chance of victory, getting 2 hits ups that to 75%. So the 2-1 play gives an overall chance of victory of 37.5%. Finally, something better than spreading out. But hang on, tripling up has a chance to win the game in round 2. Only a 25% chance, but still a chance. And if the team misses, they still go to round 3, though they'll only have a 25% chance of victory there. So what's the total chance of victory if they triple up at this point? 43.75%. So to review, if round 2 starts with 1 or 2 bonks on the solo player, the best option for the team is to spread out. If round 2 starts with no bonks on the solo player, the best option for the team is to triple up. Now we rewind back to round 1, which always starts the same. the solo player hasn't been bonked yet. What's the best play in round 1? If the team spreads out, they have a 75% chance of getting the hit, which leads to a 62.5% chance of victory in round 2 if they spread out again. But they have a 25% chance of missing, which means they should triple up in round 2 for a 43.75% chance of victory. We don't have to use the probabilities from round 3, by the way. Those are baked into the win chances for round 2. So spreading out in round 1 leads to a 57.8125% chance of victory. That's better than a coin flip, but let's see if we can get it even higher. If the team triples up in round 1, they'll win immediately 25% of the time, and 75% of the time they'll go to round 2 with 0 hits. If that happens, they'll want to triple up again for a 43.75% chance of victory. So tripling up in round 1 leads to victory 57.8125% of the time, the same as spreading out in round 1. Okay, so I know what you might be thinking right now. What you do in round 1 doesn't matter. The two extremes lead to the same chance of victory. All that matters is how you shift your play based on the results on round 1. But hang on, don't count the 2-in-1 play out just yet. If you've learned anything from math class, it should be to always show your work. The 2-in-1 play in round 1 has 3 distinct outcomes: getting 2 hits, getting 1 hit, or missing. The play will miss 50% of the time, and if it does, the team needs to triple up in round 2 for a 43.75% chance of victory. But the play also gets 1 bonk in 25% of the time, letting the team spread out in round 2 for a 62.5% chance of victory. The best outcome, however, is getting 2 bonks in round 1, which happens 25% of the time. When it does, the team will have a 93.75% chance of winning if they spread out in round 2. So how good is the 2-in-1 play in round 1? 50% chance of missing times a 43.75% chance of victory, plus a 25% chance of a single bonk times 62.5% chance of victory, plus a 25% chance of a double bonk times a 93.75% chance of victory equals a whopping 60.9375% chance of victory. That might not be super high, but when I was in school, that was a D, and D's get degrees. Wait, it's C's get degrees? Then what do D's get? What, like almonds or cashews? And that's nice. Unless you have an allergy, I guess. Do people with allergies get a consolation prize? Anyway, that means that the optimal strategy for the team is to go 2-in-1 in round 1. If they get at least 1 hit, which happens half the time, then they should spread out for round 2. But if they miss in round 1, then they should triple up in round 2. If the game goes to round 3, the team should spread out if they've already scored 2 hits, but otherwise they're going to need to bet on a 1 in 4 chance of victory and triple up. Now what if you're the solo player? Unfortunately, your only option is to play mind games, lie, and trick the other players into making the wrong decisions. Or you could stalk them, collect data on their decision-making patterns, perform a statistical analysis to determine the optimal hiding place, and then convince yourself that that's not a completely unethical way to win at Mario Party. Thanks for watching. If you enjoyed the video, leave a like and comment down below. And if you want more mathematical analysis of games of the card, board, or video variety, consider subscribing. On top of all that, I hope you have a lovely day. Bye-bye.